Hi again, everyone. So ERM was also the lead for work package 4 of HyPSTER, which was on the techno-economic assessment and roadmap towards replication in the EU for hydrogen salt caverns. So I'm going to give a brief overview of some of the work in this work package today. There we go. I'm just going to use this. So the objectives for this work package were to look at the costs and then the techno-economic analysis of hydrogen salt cavern operation. We looked at wider key enablers for the future development of hydrogen salt cavern storage as well, and then used that to inform a roadmap for replication of the HyPSTER project across Europe. So this, as I mentioned, this work package was led by ERM, but we benefited from lots of information from Storengy and ESK, informing the costs and the salt cavern archetyping. So high-level results, the capex of hydrogen salt caverns, which I'll present in a bit more detail, depends on a large number of factors, including the capacity, the depth, the pressure, and existing infrastructure as well. And I'll talk a bit more about the impacts of a few of those. We then looked at distributing the costs, the capex and the opex across all of the hydrogen served to end users to give kind of a benchmark of what might be acceptable to an end user. And we found that you could reach costs of around as low as 20 cents and maybe around €1 per kilogram of hydrogen consumed by the end user, which is notable in the context of wider hydrogen costs, but kind of potentially palatable. That really does depend on the hydrogen profile, storage profile, and I'll talk a bit more about that in more detail. And finally, we looked from a techno-economic perspective at potential suitable locations for hydrogen salt cavern development, and that included Northern Germany, Spain, Portugal, the UK, and Poland. As I just mentioned, a lot of this is highly dependent on how the low carbon hydrogen sector grows, and that could really affect how salt caverns operate and therefore how those costs might be distributed. So that's a really important caveat to a lot of this analysis. And we've tried to come up with kind of potential realistic profiles to inform that cost analysis. So, as I mentioned, there are quite a few factors that we considered, including geology, hydrogen demand, hydrogen production, hydrogen distribution infrastructure, hydrogen import and export terminals, brine disposal is also important to consider, and then the costs. So I'm going to start with that focusing on the costs a bit more, as obviously a key critical part of how viable salt caverns will be in future. So, as mentioned, a large number of factors that affect the cost, but a key one that probably doesn't come as a surprise to many people is capacity, where broadly speaking, as the size of the cavern increases, the levelized cost on a capacity basis decreases. It's not surprising that we see economies of scale with large infrastructure projects like this and large scale hydrogen projects, but that is really quite a significant difference that targeting larger scale caverns can make. Of course, that means you'd have to have the demand to sustain that. Otherwise, it doesn't make sense to develop at that kind of scale. We also considered cavern depth, whether the cavern is new and repurposed. I know Maurice mentioned the importance of considering brine disposal, which is really key in terms of viability and in terms of costs of the project as well. And then the cost of the cushion gas should also be considered. So what's making up those costs? We did a breakdown. This shows an example of one of those breakdowns where the solution mining, the cushion gas and the compressors made up a significant proportion of the capex, although there are a few other significant factors as noted there. As mentioned, this will look different if it's a repurposed cavern, for example, but this hopefully gives an idea of what that breakdown looks like. So we then distributed that across all of the hydrogen consumed by the end user. You can see at the bottom there, we're talking about quite large annual demands of hydrogen to reach these kind of viable scales. But we then do get to quite reasonable levelized costs of hydrogen. So on the left, that's divided across all of the hydrogen served to the end user. On the right, that's just the hydrogen that passes through the cavern. So obviously on the left, if theoretically you served an enormous amount of demand and not much of it touched the cavern at all, that number would be really small, but we'd have to question whether that's a realistic or sensible use of the cavern. And finding that balance between realistic profiles and palatable costs is something that we try to explore through the sensitivities of this analysis. So as mentioned, quite a few other factors to consider. We're going to talk through a few of these in a bit more detail, not focusing so much on brine disposal at this stage. And we've talked a bit about costs already, but these other 5 can really impact where hydrogen salt caverns could be developed in future. And what we've done is kind of layered all of those factors up on top of each other to find areas of interest. So we started with our geology, looking at where there's salt deposits. We then had a look at potential hydrogen demand. This obviously has a lot of uncertainty, but we tried to focus on large-scale industrial hydrogen demand, where they will need that very consistent hydrogen profile in future. And so hydrogen balancing variability in hydrogen supply from renewables will be really important. We added another layer with our hydrogen production, as well as considering hydrogen import. So there's large-scale import terminals. There may well be a need for storage to support and smooth supply there. And of course, co-location with hydrogen production could be really valuable as well. And then hydrogen distribution infrastructure. So you can see that we're talking about large quantities of hydrogen, particularly to reach the economies of scale that's needed. And so benefiting from connection to, for example, the European hydrogen backbone would be really critical for enabling these projects. So we put all of those together and had a look for places that lit up with a lot of these factors. This isn't necessarily exhaustive, so that doesn't mean that some of the areas we haven't highlighted aren't viable. I mean, HyPSTER isn't highlighted, but we know that's already happening. It also doesn't mean that these are necessarily places that are going to work. As we mentioned, there are other challenges like brine disposal, like a lot of uncertainty with infrastructure that may mean that these don't work out, but they could be really interesting based on kind of those key enabling factors. So I won't go through all of these in detail, but I just wanted to highlight a few of these. Of course, they all have the geology needed as a prerequisite, but then quite a lot of potential interesting infrastructure going on, quite a bit of production and demand in most cases as well. And that means that in these places where there's a lot of hydrogen activity, it's highly unlikely that it all works out, that the supply and demand matches exactly. And when we're talking about these large scales, salt caverns could be really valuable for helping with that. So I'm going to pause there and welcome any questions. I think I've got 1 minute.
Thank you. Thank you.
Hi, I'm Garance Vedil from Geostock. Can you please go back on the previous slide, if you mind? Thank you. I was wondering regarding like the geology and the salt deposits and everything, what kind of bibliography did you use for that?
Yeah, that's a great question. So there's quite a bit of publicly available information on salt deposits in Europe. I don't have the exact references to hand, but I'm happy to include those in the footnote of the slide. I do appreciate there's some uncertainty around that. So not all of these are necessarily backed up by borehole data in all cases. So there is some uncertainty with that. That would be a part of a future study that would be really valuable. But yeah, it's all from publicly available sources. I'm happy to send those over or put them on the slides when we publish them.
Yeah, okay, thank you.
Okay, we have another question.
Thank you for your presentation, very interesting. I am Amalia Pizarro from the International Energy Agency. I have two questions. You saw kind of some cost disaggregation, but could you tell us how much can the cost decrease when using a repurposed natural gas cavern instead of a new one? You mentioned it was possible to get the data. And then in your assumptions, how many cycles per year have you assumed? Because that will have a big impact on the cost. So if you can maybe share some insights on that.
Yeah, absolutely. So on the first question on repurposed, I am afraid I don't have that graph with me, and it depends a bit on the scale, but we looked at kind of reductions of maybe up to about 40%. There's a bit of variability within that. Then on the question about, disaggregation, on number of full cycles. So they're not necessarily full cycles is the first thing to say. We're not necessarily filling and emptying multiple times per year in its entirety, but in total, there's a bit of a range here, but it's of the order about 5, say, so it's the equivalent of 5 times the capacity passing through the cavern at one time. There's quite a lot of variability in the numbers there with the different scenarios that we run. It could be often a bit lower than that. I think 5 is probably the upper bound. But yeah.
Thank you, Felicia.